by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Welcome to Jefferson Lab. I have the pleasure to invite you to our laboratory, and I have the particular pleasure to introduce to you a quite unusual speaker. Professor Carolyn Meyers is a native of Newport News, but she has a very distinguished career up to now, and we are expecting great things from her from here on out. She is the Dean of Engineering at the North Carolina A&T University in Greensboro, North Carolina. Dr. Meyers got her PhD from Georgia Tech in the School of Chemical Engineering and Metallurgy, and also got a Master's of Science degree in Mechanical Engineering from Georgia Tech. She earned her bachelor's from Howard University in Washington, D.C. She is a recipient of many awards, but what struck me as one of the early indicators of a great career is the Presidential Young Investigators Award. That is an NSF, now an NSF award. It used to be a White House award for some time, and I can't distinguish whether you got it still under the White House or NSF. And she also got the NSF Faculty Award for Women, among many others. She has been elected to the Honor Society of Sigma Xi and Phi Kappa Phi. You aren't surprised that she is active in many professional societies. She was the president of the Atlanta section for Society of Women in Engineering. She is currently assistant vice president for Region 11 of the American Society for Mechanical Engineering. And of course, she's a fellow of ASME. She has served on the advisory board for NSF, and she has served on committees from the National Research Council. I could go on, but I will stop to here and just say, again, it is no surprise that she leads a very active life in the community, and as I said, she is a native of Newport News. Help me welcome Professor Carolyn Meyers.
Thank you, Dr. Grunder, for that kind introduction. I'm a native of Newport News, as you said. I really regret my mother isn't here. She would just love you, saying all those nice things about her kid. But thank you so much, and thank you for inviting me to participate in this Jefferson Science Series. And as you know, I'm going to talk tonight about the mechanical properties of soda cans. I'm a mechanical metallurgist, and I enjoy working with metals. In fact, one of the things that I usually like to do, and I just moved to Greensboro not too long ago, is wear some jewelry that's metallic, and I like my titanium jewelry and left it there. But I really can't understand why anybody isn't thoroughly fascinated with stresses, with strains, and with the world of metallurgy. To talk about mechanical properties here, first of all, we have to have a basic understanding of the origin of mechanical properties. Mechanical properties actually are experimentally derived from testing a round tensile bar or flat tensile specimen, exposing it to a load, and tension means we're pulling it, okay? We attach strain gauges to measure the displacement in a specified area. If we divide the load on the bar by the original area, we have the engineering stress. If we take the final length, as we increase the load, the bar stretches, and eventually it necks and breaks, and we'll see that later. But if we subtract the final length from the initial length and divide it by the initial length, we have the engineering strain. and we can plot what we call stress-strain curves. And these types of curves describe the mechanical behavior of most engineering materials. Now, there's some typical properties that we can get from a stress-strain curve. Okay, most metals, when you stretch them for a certain amount of time, if you release the load, they'll spring back to the original length. The strain will be zero. We call this elastic deformation. If the load increases and you release the load and it doesn't go back to the original length, then we know that some plastic deformation has occurred. Plastic deformation is a permanent change in shape of the material. Okay? So a typical stress-strain curve for a metal looks like this. It has an elastic region, and then it starts curving over. This part we call the flow curve. Okay? Where it starts curving over is usually very, very hard to determine, so we take a permanent amount of strain, 0.2%, and draw a line parallel to the linear part, and where it hits the curve we call the yield strength of the material, the 0.2% offset yield strength. So here's the yield strength of the material. We'll notice that there's a maximum load, and after that, continued straining occurs at what appears to be a decrease in stress. Okay? At the maximum load, if we divide that by the original area, we have a property that we call the tensile strength. And that really defines how much uniform deformation we can have in a material, and you're going to see some examples of that. And beyond that, we have local deformation. Some parts are stretching more than others when it starts going down, and then it eventually becomes so thin and so weak that the cross-section can't carry the load, and we have fracture. The stress at which this occurs we call the fracture stress. Now, if we look at this curved part of the stress-strain curve, it follows a relationship that looks like this, except this time we're using true stress and true strain. Now, if you look at this, something ought to be apparent to you. If a bar is elongating, just imagine it, and remember that volume is conserved, then the cross-sectional area has to be changing. So that's the difference between engineering stress and true stress. True stress gives you the load over the instantaneous area. Okay? And true strain really is just taking delta L over L instantaneously, and a true stress-strain curve will actually continue to increase. But the engineering stress-strain curve is most commonly used. Okay, now different materials have different strength coefficients. And different what we call strain hardening coefficients. Okay? So, just to give you an idea, here's pure aluminum at the top with a strength coefficient K of 25,000 psi, a strain hardening exponent of 0.20. We look at a typical low carbon steel, 3 times the strength coefficient. Okay? And also the strain hardening exponent is larger. So we know that steels are generally stronger than aluminum. Okay, now aluminum is one of my favorite materials. One of the reasons why is because I spent 5 years of my life on my thesis working with aluminum, not the aluminum alloy that's used for beverage cans, but with a cast aluminum alloy. When we think about aluminum, it has a lot of just wonderful, wonderful properties. One of the most attractive of which is that it is abundant, and it's recyclable. It also has a very, very high strength to weight ratio, which is nothing more than the tensile strength divided by the density. And it falls into a category of materials that we call non-ferrous materials, not based on iron. Metals we break into 2 broad categories: those based on iron, your steels, your cast irons, and those that are not based on irons, your aluminum, your nickel, your titanium, your zinc, your copper, your lead. So aluminum is one of the non-ferrous materials. And generally, non-ferrous materials, as we saw from just a chart with strength coefficients, are not as strong as ferrous materials, but they're used for the other attractive properties. One of these is the light weight of aluminum. Also, aluminum is an excellent thermal conductor, and this is why it's used in cookware a lot. Another example of a non-ferrous material being used for a particular property is zinc. It has a very, very low melting point, and for that reason it's used in a lot of die casting of intricate parts or really in toys. Some other properties of aluminum. Its atomic number is 13. Its atomic mass is 26.98 grams per mole. As we said, it has a high strength to weight ratio, ultimate tensile strength, the top of the stress strain curve divided by the original area over the density. The low melting temperature makes it energy efficient to cast aluminum, near net shape manufacturing. It's pretty soft, as you can see from these cans. It has excellent corrosion resistance. Who would want to drink a Coke out of a rusty can? It has high heat and light reflectivity, good formability, we'll talk about that a little bit later, good electrical and thermal properties, non-toxic, non-sparking, and non-magnetic. Now, when we talk about aluminum alloys in general, we divide them into two categories. Those that are used in the cast form, that is, they're poured from the molten state into a mold and allowed to cool, okay? And those that really come from a billet, which is also cast, but then they're rolled into sheets and plates or drawn into bars and tubes, and these we call wrought. So here's the designation of wrought and cast aluminum alloys, just for you to look at. Now you see, for this category of materials, the designation system from ASTM, American Society of Testing Materials, gives you 4 digits for the wrought materials, 4 for the cast, but with the cast ones, after the 3rd digit, there's a decimal point. Okay? So, looking at the temper designations, this 4-digit code indicates here, looking at this chart, the principal alloying agents. Aluminum, like with most materials, on the addition of an alloying agent, another element, improves its properties. This is why we alloy. Aluminum does not have what we call complete solid solubility. It shows a limit of solubility. And that can be used to our advantage, particularly in our cast materials and also in our wrought materials when we do the temper treatments. Okay? So this is a designation system for wrought and cast aluminum alloys. Okay, now the aluminum alloy that we use for a beverage can is alloy 3003, and it starts out in the annealed condition. Okay, and when I said it starts out in the annealed condition, one way that we control properties in alloys is by chemical or mechanical or heat treatments. And that's what these temper designations mean. Your F temper, for instance, no special treatment, nothing's done to it. Your H temper is strain hardened, followed by 2 digits, and it tells you, the first one indicates a specific heat treatment, 2, the amount of work hardening, how much formability do you have, inverse of that, really left. And here are some H designations. O is annealed. This is the softest condition, and this is where we start with the cans. The T tempers are usually special treatments to give us special properties. One of the ones that's used most often is the T6 temper. Now remember, I told you that aluminum doesn't dissolve other metals totally. The nickel-copper system dissolves infinite amounts of each other, form a complete range of what we call solid solutions. Aluminum has limited solubility. What I mean by that is everybody's had the experience of sweetening tea, and it's only, especially unsweetened tea, that you get in restaurants when it's cold, okay? And there's only a certain amount of sugar that the tea will dissolve, okay? And once you pass that limit, the rest of it settles out as a separate and distinct entity. And that's what happens when you add more than 1.5% manganese to aluminum to make alloy 3003. It can't dissolve more than 1.5% manganese. Now, we can use this to an advantage. If we look at the T6 temper, particularly for a cast alloy like 357, which is used for a lot of structural applications, a lot of aircraft applications. There was a Navy plane that we were working on that had a cast 30-foot bulkhead of A357 in the T6 temper. So all we did was by treating it, by tempering it, which is just a heating and cooling cycle, we changed the properties. We know that in the normal condition, we can't dissolve much silicon, for instance, and much magnesium. This is A357 is an aluminum silicon magnesium alloy, 7% silicon. The solubility is 1.2%, so the rest of it's left there. One way that we can increase the solubility is to do the same thing when you make tea at home. You heat it up and you add the sugar when it's hot. So we heat the metal up and we increase the solubility. This is in the solid state, however. These are solid treatments. We're not remelting it. We've already shaped the part. We heat it up. But even in the solid state, as the temperature goes up, atoms can add themselves to the lattice of aluminum and form a solid solution. And those that are outside of the lattice, then actually on quenching and reheating at a lower temperature, that's the aging treatment, the artificial age, come out in a preferred way, which makes deformation hard, which makes the alloy very, very strong. Also, another advantage of the artificial aging and the whole T6 temper is that it improves the ductility, makes the stress-strain curve go out longer so that there's more deformation prior to fracture. The last thing you want in an aircraft part is for it to break. Okay? So this is why the tempers are used to change the microstructure, and the point I want you to get is that it also changes the properties, the mechanical response of the material. So there are lots of, as you see, temper designations here. Okay, now getting back to properties. Aluminum and its alloys, if you think of modulus of elasticity, it's nothing more than stiffness. And again, we know that aluminum's a lot softer, for instance, than steel or titanium or tungsten or iron, but not as soft as lead. Okay, the elastic modulus, if we go back to the stress-strain curve that we had before, is nothing more than the slope of the linear part of the stress-strain curve. That's the stiffness or the elastic modulus of the material. So here's aluminum compared with other metals as well as with ceramics and with polymers that we know are usually not as stiff unless they're very, very highly cross-linked or treated. Okay, looking at the yield strength and the tensile strength, again, aluminum in the annealed condition has a very, very low yield strength. That means that we can change the shape with a minimum of energy and force, a very, very low 4,000 pounds per square inch stress. And the tensile strength, the limit of uniform deformation, the peak in the stress-strain curve is 10,000 psi or 69 megapascals. Again, we can look at a low-carbon steel, which is like a 1020 steel, and we can see again the big difference between the aluminum and the low-carbon steel in terms of yield strength when plastic deformation begins and how much stress it can stand for uniform deformation. This is the tensile strength. Okay, now, in the manufacture of beverage cans, we're looking at aluminum alloy 3003. And this is what it looks like in terms of composition. Just a little bit of silicon, a little bit of iron all the time, trace amounts of copper. The major alloying agent is manganese with from 1.1 to 1.5%. Again, if we think of ways to harden an alloy like this one, we're talking about what we call a single-phase alloy. So in other words, all the sugar is dissolved, and it's not distinct. It's not settled out at the bottom. It's in solution, okay? So the only way that we can harden materials like this is by working it or by controlling the grain size of the material. Okay, now to make a beverage can, we're starting with sheet. And we're going to punch it out until we elongate it all the way up to here. Okay? So that's a lot of deformation, a lot of strain hardening that's going into the material. Okay, now some of the uses of this alloy in addition to beverage cans are cooking utensils, as I told you, storage tanks, awnings, furniture, roofing and sidings, highway signs, anything that requires moderate strength and a lot of formability, a lot of deformation, a lot of change in shape. If we look at alloy 303 and compare it with, again, a low carbon steel, for 303 with a little bit of manganese, we've got a tensile strength of 16,000 psi, a yield strength of only 6, a percent elongation in the gauge length of the tensile specimen is 2 inches of 30, and a modulus of elasticity of 10. And you can see how it compares. The only place that it's close is with percent elongation with the steel, with the low carbon steel. Okay, so let's go on now and talk about the manufacture of the aluminum beverage can. It starts out as a 20,000-pound ingot. It ends up as a 3-ounce can. Okay? This ingot is probably continuously cast. That means the molten metal is put on a chilled substrate and pulled out through water jets, literally. So a solid skin forms as it passes through this cooling chamber. And you can have billets very, very large. One facility of Alcoa's, for instance, in Alcoa Center, Tennessee, which is right out of Knoxville, Tennessee, produces these billets at about 30 feet long and about 10 feet wide and about a foot deep. And they come out of these huge vats of molten aluminum, pulled through a cooling chamber until a hard shell forms, and they're pulled on off and rolled on to the next cycle. Now what happens is that they go through a series of what we call rolling mills, and in these rolling mills the billet is flattened out, and all that happens is something like this. Actually, the billet gets flatter and it gets longer because they have constraints on the side of it. So it's 2 sets of steel rolls. Here's the billet where it comes in. Here's where it comes out. Okay? In this case, we're seeing that the billet is getting wider. It's probably compressed from the top, just looking down on it. But in the case for aluminum cans, it's just getting flatter and getting longer. Now what we're doing when we put it through the rolling mills, we're doing it when it's warm, so we're allowing some healing to occur. It's fully solid, but we're allowing some healing to occur internally. The reason we want to do it when it's warm is because after casting, we have what we call an equiax, more or less, grain structure. We also have a lot of defects in the material, which act as stress raisers, as sharp areas that can start, say, a tear or what we call precipitate fracture. So we're allowing some of these defects to heal in the material as we roll it. And we're producing also a different microstructure. The grains go inside, if we were to look at them, from looking pretty much like this. And after rolling, these are the rolls. They're going to come out elongated and flattened. Okay? And also any little holes, voids in the material will also be healed. So this 20,000-pound ingot then is rolled into a 0.0116-inch sheet. Okay, it's never going back to being a 20,000-pound ingot again. Why? Because we passed the yield point of the material. We're now in the area of permanent deformation. Okay? We're in the region of what we call uniform deformation, from the beginning to the end there. And we've had a permanent change in the shape of the material from being, say, 20 by 10 by 12 to maybe being, say, 50 feet long, the first pass, by maybe 5 by another dimension. So what we've done is change the shape. We had to exceed the yield strength of the material. Okay? Now, referring to the tensile specimen that generated the stress strain curve, it looks just like a flat bar or a round section of this could be a cylindrical section on a circular tensile bar. This is your gauge length. When we look at the stress strain curve here, during the elastic part, the bar is stretching uniformly along its length. Okay? Once we reach the maximum load here, it tends to deform more in a local area than along the whole length. That we call necking. So this is where necking starts, at the top of this curve. And the cross-section then becomes smaller at a much more rapid pace and a lot longer and eventually breaks off. Okay? So what happens then during this rolling, to get this sheet that's 0.016 inches, it's going through a series of rolling mills and getting thinner and thinner and thinner and thinner. Okay? So finally we get this sheet that's 0.016 inches, and then we start another process that we call blanking and drawing. We start out with a blank, and it just kind of like punches out a 5 by 5 inch disc. And then another punch, and I'll show you a picture of it in a minute, actually forms a draw cup. This is the first step. This was a flat, cylindrical 5.5 inch disc. Then a punch comes down the disc and makes it into the blank draw cup. So then drawing then as a process refers then to the formation of a flat metal sheet into a hollow or a concave shape, such as a cup, and all you're actually doing is stretching the metal. Again, you have to have exceeded the elastic limit, or else when the punch came out, this would go right back to being a flat plate. We permanently changed its shape. That's what we call plastic deformation. Now the process of making aluminum cans is what we call deep drawing. And that's deep drawing because the depth of this draw here is actually going to end up being greater than the diameter. And that's what we call deep drawing. So what happens then, this blank, this 5.5 inch disc forms a 3.5 inch cup. Here it is, and here's the wall thickness of 0.0041 inches. And this is what it looks like, kind of. There's a punch, quite literally. Here's the blank, the flat 5.5 inch disc. This punch comes down and pushes it into this shape, stretches it into that shape. Okay? Okay, now, we still don't have a whole aluminum can here. So what we do then is use what's called a body maker, and we keep on drawing and redrawing the cup. Punch, keep on punching, successive punching cycles. This is the final redraw here. Now it's a 2.6 inch diameter can. The diameter of the final can of Coca-Cola, Mountain Dew, Pepsi-Cola, whatever you like. Okay? So again, this is just a continuation of the drawing process. Some of the properties that have, factors at least, that affect this process are the properties, of course, of the metal. If you had a piece of glass and you put a punch in it, glass is a ceramic, it would break. If you had a piece of very brittle material, very, say, high strength aluminum with very little ductility, and you put this punch in it, again, instead of stretching, we would induce cracks and failure. Okay, so the properties of the sheet metal. Also, we have to be concerned with the ratio of the blank diameter to the punch diameter. We have to be concerned with the corner radii, so they're not so sharp that they actually puncture the material. And obviously, because we're pushing like a plunger, if you will, on top of this plate, we've got some friction and lubrication problems. So these are some of the things that we have to think about in this process. Okay, so now we've got the final 2.6-inch diameter can. And the next thing we do is iron this can. Not ironing in the traditional sense. But we really want to change the sidewalls from 0.012 inches to 0.0042 inches. And we want to bring it up to the full length. We don't want to change the diameter again. It's called an ironing process. Again, it's kind of like a pressing, if you will, process, in that if you look at this schematic here, here's the die, here's the side of the cup, here's a punch, and you've got a die on. The die and the punch are going up the walls, thinning them out, and elongating them in each iron, each ironing pass. So ironing then is the name that's given to a process of thinning the walls of a drawn cylinder by passing it between a punch and a die. Here are the walls. And see how it's thinner here? Is it thicker here where the die hasn't moved up? As the die moves up, the walls get thinner, and also the side walls actually get taller. Okay, so this is the fourth step in the manufacture of the beverage can. Okay, now we've got to prepare the body for necking. Okay, so here we are. Let's see, this is after the third iron. So here we are, excuse me, after the last iron. And then we have to trim it off first because we want a certain height of the beverage can. We don't want uneven beverage cans. And how are you going to put a lid on something this crooked and uneven? And who would want to buy a soda out of a can that looked like this? Okay, so we trim it off. It's a metal finishing operation. Then we start locally deforming the can so that it can accept the top, and that's called the necker. So where are we now on the stress strain curve? If I want, almost at the end, where do we start? That's pretty good. We're beyond the maximum load because that's where necking occurs. We've got uniform elongation, uniform deformation until we get to the maximum load. Okay, so this tells you that in this operation, the stress has to be higher than that peak in the stress strain curve to have necking. So here is the first neck. Okay, and sometimes they spin it a little bit and also continue the stress and give you the second neck. Okay, so I'm sorry, this is the second neck. Let me put a flange on it, and it can accept then the top of the can. Okay, so looking back at the steps in the manufacture of the aluminum beverage can, we start out with the casting process. Then we go to a rolling process through a series of rolling mills. The rest are basically cold or warm work processes in which we are doing a series of drawing operations, a series of drawing operations to give the basic shape, to get to the final diameter, to form the cup. Ironing to thin out the sides and give us the length that we want. We do some more machining to prepare it for local deformation and to give us a uniform height. We do some local deformation at the top of the can to give us the surface that we want to accept the lid. So this is the manufacture of the aluminum beverage can. Now, you know I'm a teacher, probably, and I don't have a class this quarter. So, who can tell me now, why is aluminum used for beverage cans? Why don't we make them out of lead? Why don't we make them out of steel? Why don't we make them out of nickel?
Because they don't rust this quickly.
She said they don't rust as quickly. That's right. Another?
It's abundant.
It's abundant. Yeah.
It's recyclable.
Recyclable. Good.
Non-toxic.
Non-toxic. What else? Tell me about processing. It's easily shaped. Thank you. So what does that mean? Cheaper to make. Very good consideration. Okay. Less energy to make because it has what? Low stresses for permanent deformation. The more stress you have to put into the forming operation, the more expensive it is, the more energy is used.
You can use it again.
You can use it again, recyclable. Yes. Okay. So are there any questions?
How do they put the ribs in the cans? Like on some cans, how they have ribs?
The ribs in them? Again, they're just picking selected areas, and they're like, where are you? Oh, okay, I saw you and then lost you. Okay. They're picking selected areas and exceeding the maximum load and causing local deformation, necking in those areas, just like here at the top. Okay.
How fast, how many cans per minute or how fast does that go?
The copper, I remember, can do 14 cups per minute. Let me check that. Wait a minute, I wrote that down. So I knew somebody would ask me that. Yeah, the copper produces 14 cups per stroke at 250 strokes per minute. That's just to form this part out of the 5.5-inch disc. 14 cups per stroke at speeds of up to 250 strokes per minute. So 14 times 250 will give you how many cups per minute? Okay? It's a lot of cups. Okay. The lid is, well, oh, got the wrong one. It's filled, the lid is stamped out. And then it's press fitted on. And yeah, after filling.
Does some of them need to be annealed during the process?
Most of this, and I actually checked with some friends of mine at Alcoa, most of this is done, as I said, is warm working. So that's that continuous anneal as they're doing, and not hot working, and not really cold working, because this is a whole lot of deformation. But it can be done in the warm working regime. Okay, and what that means is that any defects that are created in the microstructure as a result of stressing it, and that's all this is doing. All this is doing is stressing the material. That's why when you see the stress strain curve, it goes up like this. Continuous. Should have made this more linear here. Continuous increase in stress to keep deformation going. We're actually changing the microstructure, creating little defects. And the question that he asked is that these little defects would tend to make it harder and harder to deform the material, which it is. It also tends to shorten the time to fracture. So what you typically do is keep it warm so that with increased warmth, the atoms will tend to, atom mobility increases with temperature. So some of your defects, the atoms will rearrange themselves to eliminate some of the defects. Okay? And so if you do it in the warm range, this rearrangement is occurring while the deformation is occurring. So you're minimizing the effects of the defects. Most of this is warm to cold working. The rolling is done when it first starts off hot and cools with successive rolls.
What about the reactability of it after you get it made there, reacting with the content, such as the acid, carbon acid of the soda?
Generally, this is one of the
cans sometimes.
I'm sorry?
Sometimes they coat them.
Sometimes they coat the cans.
But then,
one of the advantages of aluminum is it's generally not reactive. I don't know anymore about he asked me about what about the reactability and the coating of the cans.
Let's see, you have a slightly there because you got a tremendous pressure being produced.
That's right.
Along with the acid in the can reacting with the atoms there.
Mm-hmm.
Yeah.
Don't know.
How much does each can weigh, would you say?
It weighs 3 ounces. Starts as a 20,000-pound billet. Yes?
Okay, by the time that we get a soda can, is color coded? How do they do the color?
The color is usually done with kind of an anodizing and painting treatment. It's a chemical reaction, a chemical dye that's sprayed on that adheres to the aluminum. You know, you can't really scrape it off, but it's like a surface. How can I explain this? It's like a surface treatment. Okay, that's the
Plating? Type of plating?
well, in some cases you do plate or clad aluminum, like alclad aluminum.
Mostly anodizing the dye?
Yes,
Anodizing dye?
yes.
Yeah.
It's a electrochemical process to put an oxide coating on it.
Well, that's one of the reasons that you know, aluminum is chosen, because it forms, first of all, it's non-corrosive and forms a tight oxide layer, and then it's easy to accept other types of layers.
With modern technology as it is, do you think eventually they'll go to the 24-ounce can of soda?
24-ounce can. Well, I guess it's possible. I just can't imagine wanting to drink a 24-ounce soda. You know?
24 ounces of other stuff.
Yeah, I understand. But then, you know, if you think of the economics of it, you got to change an awful lot of vending machines to handle 24-ounce cans, you know, and so that would be expensive too. So it's more than just the metal and the processing, it's the economics part too. But I guess if there's a demand in the marketplace, it could be done. It would have to probably start, I'm sure, with a larger blank, more draws, and more ironing stages to get the height. Somebody's in the back? Yes.
How long did you study aluminum?
Well, I didn't study aluminum 303. I studied A357 for 5 years for my doctorate, and then I worked in it in research for about 5 more years.
Why did you choose that?
Well, I'm fascinated with big things, I guess. Airplanes and cars. 357 is kind of a workhorse cast material that's used in a lot of military aircraft. 390 I've also worked with, which is another cast aluminum alloy, is the basis for your engine block. So I kind of study the materials that fascinated me, and aircraft materials and automotive materials fascinate me. I've also, the only wrought alloys that I've looked at, and I generally study how we predict properties from, as a result of heat treatments, are 7071 and I think it's 6065. It's been a while now, but 7075 and 6061. That's the way it goes. Again, they are structural alloys that are used, again, in aircraft body parts. And that's just, I just had the opportunity to study those, and I like airplanes, I like cars, and that's why.
Are cars made out of aluminum?
Oh, yeah. Well, you know, a lot of, it's amazing. I sit here and look at you and think of when I was in high school and I had my first learned to drive, at least. I won't tell you how long ago that was, but cars are much, much heavier then. One of the reasons was that they had a whole lot more cast iron, and now they have a whole lot more aluminum and polymers, or plastics, I should say, not polymers, but plastics in them. As you know, the trend is toward a lighter weight car. And aluminum has this high specific strength, or strength to weight ratio, and that's one of the advantages. The 390 engine block has been used quite a bit, and is in many cars. Much lighter than a cast iron, just as durable as the cast iron block. Gives you better fuel efficiency.
Yeah, I was going to ask about that expansion.
Are there any more questions for our speaker? We have one here.
Okay, she said 357 would be what? She said that 8357 was used to make airplanes. I guess I know they use aluminum because it's lighter, but why do they use 8357?
Okay, this is my favorite material. It's a ternary alloy of aluminum, silicon, and magnesium. The reason they use it, and they use it in the T6 temper, is first of all, I'm talking about the bulkhead. This is the front of the airplane. This is a big kind of circular casting that goes right after the nose cone part, okay? It is strong in the T6 temper. It's lightweight, and best of all, it has good ductility, but most important is that it has what we call good fracture toughness. Fracture toughness is the ability to stop a crack, if you will, from becoming a catastrophic failure. And one of the things that you don't want to happen is for a crack to reach a critical size in a metal part, because then it runs at the speed of sound and you can't stop it. Okay, so you want a material that's going to dent, if you will, absorb some of that impact energy in deforming the material and not shatter. A357, because of the heat treatments and the composition and the chemical treatments, is grain refined. The structure is also internally modified with strontium or antimony, so that there's a defined morphology, if you will, to the second phase particles, excess silicon that's left. You heat treat it then so the magnesium silicide comes out, makes it real strong, and because during the heat treatment you also spheridize a lot of your intermetallics and your second phases, then you've reduced a lot of stress raises. It's got a lot of ductility, strong and ductile. Usually those two are mutually exclusive. It's also fairly cheap. The casting process, which is why it fascinates me too, is a near net shape process. Instead of all of these working operations, we can do it basically in one, pour it into the mold, take it out of the mold, cut off the casting rigging and the gates, do a little bit of finishing, and it's done. Every one of these steps is machine and energy, people intense, which drives your cost up.
Before we will thank our speaker again, I want to give her a little test.
Oh.
And I have here a little medal for her, and it is made out of a metal which was on none of her lists. And I give her a little cue. It is superconducting at 18 Kelvin.
Ooh.
Does anybody know what the metal is? Does he say no? Once again, louder. No.
Niobium.
Gold isn't superconducting. It's niobium.
Yes.
Wonderful. Right?
Yes, thank you.
Okay, we want to thank our speaker again.
Thank you
for
very much.
Talk.
Thank you. Well, I've never seen any niobium.
Pardon?
I've wondered if it was niobium.
Yeah.
I've never seen it. How do I turn this off here?
Yeah. No. If somebody has a special question to our speaker, please come to the front.
So this is niobium.
Oh, don't ruin your finger like that.